In this installment, we're going to talk about estimation of a population parameter. Now we'll first start off talking about point estimation. A point estimate is a number that represents a guess as to the true value of the population parameter being estimated. Now this number, this point estimate, will hopefully be close to, but will probably not be exactly equal to, the population parameter being estimated. The reason that it probably will not be exactly equal to that population parameter is that it's a statistic. It is computed from a random sample, and therefore it is a random variable. And because it's a random variable, it varies from one sample to another. And so because it's varying, it will probably never be equal to the population parameter that we're trying to estimate. But hopefully it will be close to that parameter. Now, because it's a point, because it's a single number, it's a very, very precise value. All right, you can't get more precise than a single number. But again, we understand that because it's a statistic, it's a random variable, it's probably not exactly equal to that population parameter. Now, on the other hand, there is what is called a confidence interval estimator. Now, a confidence interval is a range or interval of plausible values for the population parameter being estimated, along with a measure of the reliability of the estimation procedure itself. Now, this measure of reliability is called the confidence level and is typically expressed as a percentage. Now, because a confidence interval is a range or interval of values, it's not as precise as a point estimate. But associated with this confidence interval, we do have a high degree of confidence that the parameter being estimated is actually contained in the interval. So we're trading precision for confidence when we move from a point estimate to a confidence interval. Now, the confidence level, also called the confidence coefficient or the level of confidence, this is something that we choose. We choose the confidence level that we want when we construct the confidence interval. Some typical confidence levels would be 90%, 95%, 99%. And once we construct an interval, we can say that we are, for example, 95% confident that the interval contains the parameter of interest. Now, it's important that we interpret the confidence level correctly. It is not the probability, the conditional probability, that the confidence interval contains the parameter being estimated given the data. It's more of a measure of the reliability of the procedure used to construct the confidence interval. So if we think about it from the perspective of before we've sampled the population, and the goal of our experiment or sampling procedure is to select a sample that we can then use to estimate a particular population parameter, then if at that point, before we sample the population, if we ask the question, what is the likelihood or what is the chance or the probability that we get a hold of a sample for which that confidence interval that we construct from the sample will contain the parameter that we're interested in, then at that point we can think about it as a probability. Because at that point, we're thinking about the procedure itself, not a specific interval that's already been obtained. Now, in many situations, in particular, when using procedures that are based on the normal distribution, we construct the confidence interval by starting with a point estimate of the parameter of interest, and then we compute the lower and upper confidence limits for the interval by moving a certain distance to the left and to the right from that point estimate. So the point estimate is our starting point, and then there's a certain distance that we go to the left and to the right of that point estimate to get the endpoints of the confidence interval. So when that is the procedure that we use to construct the confidence interval, that distance that we go to the left and to the right is called the margin of error for the interval. And so we can think of this in a couple ways. We can think of the margin of error being half the width of the confidence interval, or we can think of the width of the confidence interval being twice the margin of error. Now, if we are using non-normal based procedures to construct a confidence interval for a particular parameter, for example, if we are constructing a confidence interval for a population variance using the chi-square distribution, then the procedure for constructing that confidence interval does not fall into this kind of framework. And so in that kind of a situation, we really would not be talking about a margin of error. But for those situations where we do follow this general procedure, and one example of that would be constructing a confidence interval for a population mean, then in those situations we do talk about the margin of error. Now, the confidence level of a confidence interval is expressed in general in the following way: 1 minus alpha times 100%. Now, for those situations where the sampling distribution of the point estimate is at least approximately normally distributed, then the confidence interval will be of the following form. We will start off with a point estimate, and then we will go a distance to the left and to the right to get the endpoints, and that distance, again, is the margin of error associated with the point estimate. Now, the formula, the general formula for the margin of error, is given by the following expression. It's the product of what we would call an interval coefficient, in this case a z-value, a value from the standard normal table, and the standard error of the point estimate itself. So again, when we construct the confidence interval, we start off with a point estimate, and associated with that point estimate is a standard error. That's what we're talking about right here. All right, so the margin of error is equal to the standard error of the point estimate times the interval coefficient. Now, the interval coefficient, for example, in this case, a z-value, again, this is coming from the standard normal table. And in general, the notation z sub p, which I've got listed here, is defined to be a number on the number line such that the area under the standard normal curve to the right of that point is equal to p, whatever's in the subscript. And so this is how we would express that definition in terms of probability. So in particular, this interval coefficient for a two-sided confidence interval, all right, where the interval coefficient comes from the standard normal distribution, this would be the number on the number line for which the area under the standard normal curve to the right of that point is equal to what's in the subscript, which in this case is alpha over 2. So this is the general form for a confidence interval for a parameter when the sampling distribution of this point estimator is at least approximately normally distributed. So let's look at the relationship between the confidence level and z sub alpha, and in particular, let's look at how to calculate the interval coefficient z sub alpha over 2 for various confidence levels. And so we'll consider three confidence levels, 90%, 95%, and 99%. So if the confidence level is 90%, then recalling that the confidence level is expressed in general as 1 minus alpha times 100%, that would imply then that 1 minus alpha is equal to 0.9. Therefore, alpha is 0.1. And so alpha over 2, which is the quantity in the subscript of our z-value here, that would be 0.05. Right? And we'll look up and see what that interval coefficient would be in just a second. But moving on to the confidence level of 95%, in that case, 1 minus alpha would be 0.95. Alpha would therefore be 0.05. Alpha over 2 would be 0.025. And so the interval coefficient for a 95% confidence interval would be z sub 0.025. And then finally, for a 99% confidence level, 1 minus alpha would be 0.99. Alpha would be 0.01. Alpha over 2 would therefore be 0.005. And so the interval coefficient for a 99% confidence interval would be z sub 0.005. Now, the values for these interval coefficients we have here. So z sub 0.05, the interval coefficient for a 90% confidence interval, is 1.645. The interval coefficient for a 95% confidence interval, z sub 0.025, is 1.96. And the interval coefficient for a 99% confidence interval, which is z sub 0.005, would be 2.575. And so one thing I want to point out here is that as the confidence level increases from 90% to 95% to 99%, notice that the interval coefficient is getting larger. 1.645 to 1.96 to 2.575. Now let me go back a few slides to where we had the formula, the general formula for the margin of error. All right, you'll recall that the margin of error is equal to the product of the standard error of the point estimator and the interval coefficient. And so what we see here is that as the confidence level increases, the interval coefficient is increasing, and so therefore the margin of error increases as well. And so what does that tell us? As the confidence level increases, because the confidence interval width is twice the margin of error, what that tells us is that as the confidence level increases, therefore the margin of error is increasing, and so the interval width is increasing as well. Again, as the confidence level increases from 90% to 95% to 99%, the width of the corresponding confidence interval would get wider and wider and wider. Now let's talk briefly about the relationship between the width of a confidence interval and the precision of that interval. You'll remember that when we talked about a point estimator, we said that because the point estimator is a single value, it's a number, that's as precise as you can possibly get. You can't get any more precise than a single number. When we start considering intervals or ranges of values, then we start losing precision. And in general, the wider the interval, the less precise the estimator. All right, and so that's what we're talking about here. The confidence interval width and the precision of that confidence interval are inversely related, so that wider confidence intervals are less precise and narrower confidence intervals are more precise. Now, one more thing I would say about this is that the more precise an interval is, the more information or the more informative it is. The less precise an interval is, the less information it provides. And so now let's talk about the relationship between confidence level and precision. Confidence level and precision of a confidence interval are, again, inversely related. You'll recall that if we increase the confidence level, that's going to increase the margin of error. And if we increase the margin of error, then the interval width increases. And based on what we saw on the previous slide, wider intervals are less precise. And so increasing the confidence level increases the width of the interval, therefore, or thereby decreasing the precision of the confidence interval. So for example, if we go from a 90% confidence level to a 99% confidence interval, that's going to increase the width of the interval and therefore make the interval less precise. Conversely, decreasing the confidence level decreases the margin of error, therefore decreasing the width of the interval, thereby increasing the precision of the confidence interval. All right. Now, I want to spend just a few moments here discussing the relationship between hypothesis tests and confidence intervals. So we have talked about hypothesis tests in general. These are procedures for making qualitative assessments about which of two competing statements represent the true state of nature. And for example, we discussed a two-sided test of this form. So the null hypothesis being that the mean of a population is equal to mu sub 0 against the alternative hypothesis that the population mean is not equal to that value. Now, that null hypothesis will be rejected at a significance level of alpha if and only if the hypothesized value mu sub 0 is not contained in the 1 minus alpha times 100% confidence interval for mu. All right, so let me state that again. And this is a very important relationship. This relationship between a particular type of hypothesis test and a corresponding type of confidence interval. And in particular, we're looking at an example of a two-sided hypothesis test. And again, the null hypothesis for this two-sided hypothesis test would be rejected at a significance level of alpha if and only if that hypothesized value mu sub 0 is not contained in the 1 minus alpha times 100% confidence interval for mu. So that wraps up what I wanted to say in this particular video about estimation, point estimation, confidence interval estimation, and then tying confidence intervals back to hypothesis tests and discussing, but just very briefly, the relationship between a confidence interval and a hypothesis test.